Hi everyone. Today we are going to discuss a problem in dynamic programming which is known as matrix chain multiplication problem. Okay. I am not going to explain what dynamic programming is or the few introductory concepts of it, but you will surely get it as we move along in the problem. So we all know how to multiply a matrix. Like this is a matrix A cross B. This is another matrix B cross C. So the necessary condition for multiplying is that the column of first should be equal to the row of the second, and then the matrix we obtain is A cross C. So what happens in this problem? We are given a sequence of matrices like A1, A2, A3, A4 and so on, and we have to like arrange in some way so that the minimum cost is minimized. We just have to find the order in which we are going to multiply. Like first we are going to multiply these two, then these two, then these two, or we can do it like A2, A3, then with A4. So our job is here to find the correct parenthesization. And how this parenthesization affects? Well, it affects a lot. As like first let me show you what is cost. Okay, what is the cost of multiplying a matrix? Then I will explain you how this thing has great effect over some other parenthesization. A single parenthesis can be 10 times faster than the other. Okay, well, let me show you the basic matrix multiplication program. Okay, so I have written the basic program of matrix multiplication. Well, it is actually the pseudocode. Most of you have already encountered this till now. So as you can see, if the column doesn't match the row, then we can't multiply. They are not incompatible. Okay, so, and this is the basic 3 loops that perform the first row multiplied to the second column and so on, and this is where the multiplication actually occurs. So as you can see, there are 3 loops, first, second and third. Okay, and let's say this our A matrix is having P cross Q dimensions, and our B matrix is having Q into R dimensions. Okay, so our first loop in matrix multiplication runs for the A row. Okay, so that is P. So we say P times whatever the inner loops are, and the second loop runs for B columns. What is B column? This R. Okay, times whatever the inner loop is, which runs for A column, that is Q. So Q. So means this multiplication occurs this many times, that is P into R into Q times, or we can say PQ R times. Okay, so this is the cost, and our job is to minimize this cost. That is, if we are given a matrix A into P into Q, so our job is to minimize this cost. Okay, if we are given a matrix A that is P cross Q, and we have to multiply it with B Q cross R, Okay, PQ cross R, then we will get a matrix having dimensions P cross R. Okay, and the cost will be PQR. Now let me show you the what is by significance of the various parentheses. Let's see it by example. We have a matrix A having dimensions 10 into 100 and B having 100 into 5 and a C having 5 into 50. Okay, so if I multiply like A, B, then C, so what will happen? See, these two are matching, so they are compatible, and I will get a matrix of this. But the cost of multiplying A, B will be, as we have seen, P, Q, R. This cost P, Q, R. So the cost is P, Q, R. That is 10 into 100 into 5, which is 5000. Let this matrix be A dash, okay, of dimensions 10 into 5. Now multiplying it with A dash into C will be A dash is 10, then 5 and 50. So 10 into 5 into 50, that will be 2500. Yeah, it was 5000, sorry. So the total cost is 7500. Now if I change the order to be like A, B, C, okay, so the cost of multiplying BC is 100 into 5 into 50. So 100 into 5 into 50 equals to 25,000. Then let's take this as B dash. Then cost of multiplying B dash with A is 10, 100 into 100. And what is the dimension of B dash? That is BC, that is 100 into 50. So the cost is 10 into 100 into 50, 50,000, and the total cost is 75,000, adding these two. So as you can see, a simple change of parenthesization created a difference that is 10 times. So whatever CPU or processor you are using, a simple change in our order of algorithm or anything can affect a lot. So as you can see, this is much better than this. Okay. Before we start to actually find the solution with the help of dynamic programming, I want you all to note that we are not actually going to multiply the matrices. We just want to find the order of multiplication. Okay, so let's move to the step 1. Step 1 is finding the structure. That is optimal substructure. we are having a chain of matrices, that is A1, A2 till AN. So, and a substructure of it will be from AI to AJ. Now, if we split this from AI to AK and AK plus 1 to AJ and multiply these two set of matrices, so our cost will be the cost of this and the cost of these multiplication of these matrices plus the cost of multiplying these two. Okay, so what we actually have to find a perfect way to split, perfect position to split, to find this AK between any substructure of matrices. That is the actual goal, actual thing that will take us to the goal, the perfect place to split, that is the optimal place. Okay, so this is the structure we are working on. Now we can, for the second step in dynamic programming after finding the structure of the problem is to find a recursive solution of it. Step 2. Solution. Okay, so what is our goal is to minimize the cost, and we are having these matrices. Let's say the cost is m of ij, be the cost of multiplying a of I to j for any substructure a of I to aj. The cost is m of ij, and finally our goal is to find the cost of m of 1 to n for a of 1 to n. Okay, so we are having these matrices ai plus 1. So the dimension of this ai, let be, is pi into pi minus 1 into pi. Okay, these are the dimension of matrix ai. So assuming that we split at a place k, the cost of m of ij can be expressed as m of 1k plus m of k plus 1 till j into, as we already know, when there are two matrices p cross q, q cross r, the cost is pqr. Applying the same here, the cost is pi minus 1 into pk into pj. Okay, as pi minus 1 is of this, pk, that is the same column, and pj is the last. So this is the cost for multiplying ai to aj, where we split at ak. This algorithm assumes that we know where to split, but that we know where k is, but actually we don't know. So we are going to find the place which gives the minimum cost. So we have to determine this k. So we can give it like m of ij, our expression changes a bit, 0 if I equal to j, that is a single matrix, no cost is there. Then we are going to take the minimum. Okay, focus on this minimum. This is the most necessary step we have taken. Okay, so m of I k plus m of k plus 1 j, this whole thing. So we are going to minimize this expression by checking all the values of I to j with k. Since this is the recurrence relation, so by a normal recursive solution will be exponential in time. But that's where dynamic programming comes into action, as in recursive there will be overlapping sub problems, like we will be calculating ai and ai plus 1 lots of time in a recursive solution. But in dynamic programming we calculate this once and save it in some memory place, and whenever this thing occurs again, we just take it from the memory and place it in our expression. Okay, now let's move on to the step 3, that is computing the optimal cost. Now we will compute the cost according to the algorithm. Okay, we are having n, that is the length which we are length minus 1 of our chain of matrices. Let m, which stores our cost, okay, and another table s, which we will be using to store. So this s will be storing our optimal value of k for the matrix I to j. Okay, so for first we initialize it 1 to n. The optimal cost be m of I equal to 0. Now for L equals to 2 to n, for I equal to 1 to n minus 1 plus L, j equal to I plus L minus 1. This is nothing, this is just simple for calculating. See, in the first recursion it will be, first loop run, it will be m of 1 1, then 1 2, and this will go on increasing. So we are using the bottom up approach of dynamic programming. So this is the loop for that, and we are specifying m of I of j equal to infinity in the start. Okay, this is the pseudo code, so this is infinity. Now for k equal to I to j minus 1, so we will be varying k, that is the optimal place to split it from I to j minus 1, and we will be calculating our cost. This is the cost, m of I of k plus m of k plus 1 j plus those scalar multiplication pk pj. Okay, if this cost, if q is less than m of I of j, then we are going to put this as the optimal value. If the k, like k is some I plus something, and it is less, this cost is less what we calculated for previous value of k, So we'll put this new cost in this, and in the other matrix we'll put the value of k, that is from ai to aj the best value to split is at k, and we are going to store it in s of ij. In the end just return m and s. So in this way we will get our optimal cost for I of j. And if you want to print the actual order of multiplication, you will get it from s of ij. Step 4 can be printing the order. So if I equal to j, print a, that is what a with I, that is a1 a2 whatever, when I equal to j, else print, call this function whatever this name is, like print matrix, okay, with the parameter s of I and j. Okay, this function, call this again, print matrix with s of I, and one thing, I of j, just increase it, s of I plus s of I j, the s I and s of I j, that is the place of k where we splitted, and the one after that print the same matrix s comma s of I j plus 1, that is the place we split, plus one more to j. So it will recursively print something like a1 a2 wherever there are brackets. So in this way we will get the actual order of multiplication. So this is having the actual order, and this gives us the cost for I to j. So in this way we have determined the optimal way to multiply a chain of matrices by minimizing the total cost. Okay, see you next time.